Good. All right, Manifesto. So there's been this golden age of reductionism, right? So there's 300 years where we started to, took a long time, but we eventually got to atoms. And it's kind of shocking, actually, how this worked out. So basically, the shovel means it's time to get to work on the next part. So good words in here. Complex, this is a good word, right? So there have been some other terms for this sort of study, like cybernetics and so on. It's a little strange. Sounds like some sort of Doctor Who thing. But complex, right? It's just folded in fold and weave. It's a nice word. Systems. Okay. So, it's not simple or straightforward. It's a bit different to this word complicated. Sometimes you'll see this. It's a good thing to say. Like a mechanical watch, this could be entirely in someone's head, right? You could make this and understand how it all works. But these things have kind of moved, some of these things have certainly moved past one person's mind, right? So that's happened with planes, right? Boeing, produces something and then all the battery, like the power goes off and no one knows why and so on, right? They have these new things they produce that fail so they can be not particularly adaptable. Power grid is, perhaps one of the best examples, right? We have all these nicely little functioning systems that you could kind of understand, and then for business reasons and all sorts of things, we start to connect them, and we end up with something that can fail globally. And so basically, any system, once you start connecting it up to many other systems, you get potentially these fantastic returns, right? But you can also, you've also now allowed for global failure, right? And so planes, right? Terrific, right? Now we can travel all over the place. I think Boeing or whatever, they're talking about getting across the Pacific in 3 or 4 hours now, right? With something that goes at Mach 5. Probably shouldn't eat any food before you get on that thing. But, that of course has given rise to global pandemics, right? I mean, there have been spreadings of diseases forever, but they're changed from slow progression that would be horse and cart speed at the most to eventually, these things that could hop profoundly. And Facebook, Facebook is a good example, right? Facebook is connected to a lot of people, and there's a lot of, you have your friends of friends, and there are an enormous number of people 3 steps away from you. Unbelievable number, right? Well, it's a huge number. So things can spread and take off, and and bad things can happen, and Mark Zuckerberg gets to apologize again, right? Okay. So that's the point here. Like engineered systems, they can become complex. So we can get into the kind of natural systems kind of thing, and then we can get these spectacular things. So people will talk about complex adaptive systems, fair enough, and that just means there's some kind of agency in there, right? So they want to be talking about, say, biology or evolution. But I like complex systems because I want to talk about fluid mechanics as well. So this is a basic definition. People are going to argue about these things, but basically a distributed system, many interrelated, size is an issue. There could be a network. There's no centralized control or limited centralized control, and has emergent behavior, right? So that there is, and this is this more is different framing of Anderson, very powerful one. There are other pieces that could be in there, right? You could have nonlinear relationships just built in. There could be these feedback loops. Networks, of course, can produce these. It doesn't have to be there explicitly. Open, like there's energy coming in, being taken out. These are other pieces. Memory, of course, matters usually in a lot of systems. And modularity, and this is actually a big feature of a lot of natural systems. There's a lot. I mean, even just say the editorial structure of Wikipedia, right? It's actually quite hierarchical. This happens over and over again, and being able to kind of extract that is a big piece. Okay, mechanisms go from being kind of physics, the sort of, gravity is like making planets and stuff, and then out to, and it's this sort of rise into algorithms. Life, the advent of life, I think, is the advent of algorithms, right? You start to get little loops and little kind of if-then statements, in a sense, and then it's algorithms increasingly sort of trying to pull itself away from physics, because physics is a problem. You got to eat food and do stuff and, go to sleep in our case. Lots of things are complex systems, really, all sorts of pieces. We like to talk about flocking of birds and ants making strings and things, but all sorts of systems. I mean, forests, this is just the last 20 years, the degree to which trees talk to each other. I don't know if any of you have seen this, and I'll try to write this. Amazing, fantastic. It's just unbelievable, really incredible sort of thing. Through the root system, and then there's all this fungus that's actually delivering the food to the trees, because it's these little highways that it's extracting minerals and so on. And pulling these the material towards trees. So you'll get some in British Columbia full of there's salmon in the tree. Anyway, so all these fields, everything, right? So everything is, because all of these fields have gone from, and this is the big piece, data scarce to data rich. And they have to eventually, and I'm not going to be able to talk about all of this. This is again, hard to read here, but this is an attempt, valiant attempt, to try to put it all together. And you can come back and sort of look at this. I've got a link to it somewhere, I think, by Brian Castellani, who's at Kent State. I just want to point out, so I've worked with a bunch of these people. Juniper Lovato, who's our education person, it's hard to read this thing. Yeah, she's here. So she's here as a complex systems education champion.